Hi. I've owed you this for a little while, so I'll give it to you. This is on fault tree analysis. Um, and this is kind of a strange thing when you first encounter it because literally what you're doing is planning how to fail. And that sounds a little strange, but engineers have to do this all the time. And why? Because systems, sorry, I'll get a good color. Systems fail. That's what they do. Um, there's no perfectly designed and constructed system. You don't have perfect components. They fail. Things stop working. And what you're trying to do is to make critical failures rare. And so, and what you want to do is achieve assurance of this in some meaningful analytical way, so that you can say with confidence that this failure will likely not occur um, for long periods of time. And so there are two primary methods that are used for failure analysis in projects. You may have heard of both of them or one of them, but there's failure modes and effects, or FMEA. Failure modes and effects analysis, as I say, is a bottom-up method. You start with individual component failures and you determine what that's going to do to your system. Um, these two definitions, by the way, are on this website if you're interested in reading more about this. Um, FDA fault tree analysis looks at faults that you don't want to happen. I don't want this to occur in my system, or I want this to occur in really, really rarely. And so you look at that fault and then you go down from there. So it's a top-down analysis and determine what individual failures or what specific failures can cause that to occur. Um, Now, each method has its advantages and disadvantages, and I say see the reference website if you want to learn more about that. FDA has the advantage of giving designers a measure of system robustness, and it's a measure that can actually be quantified. FDA uses Boolean logic and failure rates to produce a measure of robustness. Failure rates they're called failures in time, and they're reciprocals of the mean time between failure. So if you've got MTBF, if you've seen that in a component or something, then you can find the failure rate simply by taking its reciprocal. If the mean time between failures, say for example, is 10,000 hours, failures per hour is given as one failure per 10,000 hours, and this gives you your failures in time or your failure rate. If I had two systems and one was capable of taking over for the other, then the failure rates multiply. So I've got 1 times 10 to the fourth, 1 times 10 to the minus fourth times 1 times 10 to the minus fourth. And this says this would be my ultimate failure rate, 1 times 10 to the minus 8 failures per hour. You could flip that over and get your mean time between failure. Now, the multiplicative relationship like this, in other words, I've got two redundant systems, both capable of doing the task in some way. In a total failure would require that both of these systems failed. Then I represent that with an AND gate. So I've got system one, this is the failure rates are in parentheses, and system two going into this AND gate. And out of this AND gate comes the multiplication of those two failure rates. And this is the top level fault. The system's unavailable, say. Okay, now if two systems were arranged such that either system would cause a system to be unavailable, then the failure rates add. This would be the case where I had two systems, say, in series like this, and if each of them had the same failure rate, which it wouldn't typically happen, but then I combine those with an OR gate. And so that says that I've got 1 times 10 to the minus 4 failures per hour, 1 times 10 to the minus 4 failures per hour, and I add those two. And so I get 2 times 10 to the minus 4 failures per hour. Now, system using fault tree analysis, the system is analyzed again analyzed by determining top events, things that I want to happen rarely, and then I determine the lower level events that cause that top event and all their combinations, and I assign failure rates to all contributing events and combinations, and then I determine the top event failure rates. One of the things that you'll notice is that I say assign failure rates, and you go, well, how will I know? Well, manufacturers will tell you what MTBF is for components, and there are also some military specs that will allow you to do the same. Okay, I thought we'd go through an example. And my example is just a simple public address system. So I want to be able to address the public. Say this is a tsunami warning or something like that. And I want to be able to address the component or address the public, and I don't want this not to work. And so I'd like to make sure that it was very reliable. And so my top level event is that no sound comes out of the public address system. And so if I look at this, and I've got what are some possible failures that I could have that cause no sound. You know, microphone failure. If the microphone fails, I'm not going to have anything going into the amplifier, and so that's going to have no sound coming out. And so, so I could also have a power failure and amplifier failure itself. I can have a speaker failure. Now you notice that I've added some AND gates in here, and I've made my system carry some redundancy. And so in this case, I've added a battery backup. You can see that I had 1 × 10⁻⁴ failures per hour for a mains failure, and 1 × 10⁻⁵ failures per hour for a battery failure for the battery backup. And these are called root events. This is as low as it goes. But you'll notice that by adding this battery backup, I change my failure rate to something that's 1 × 10⁻⁹ failures per hour. So the system has become much more reliable because I added this battery backup. So for speaker failure, I decided to put 2 speakers in the system because I've got a 1 × 10⁻⁵ failures per hour, and these failures are just completely made up, and I'll talk about how you can do better than that in a minute. But I've got 1 × 10⁻⁵ failures per hour, 1 × 10⁻⁵ failures per hour for both speakers, but now both speakers have to fail before the system will have failed. And that says that I'm going to multiply these 2 failure rates, and I get 1 × 10⁻⁻10 failures per hour. Now what that leaves me with here is my weak link in the entire system is the amplifier. Now the amplifier isn't incredibly unreliable or anything, but if I wanted to improve this, I could put in a redundant amplifier, and I could make sure that the system was available. So that's the weak link, is the amplifier. I could fix that by adding redundancy to that. This is just a basic fault tree analysis. What I'm trying to do is look for something that I want to happen rarely in the system, determine all the causes that can make that failure occur, that fault occur, and then add what redundancy I can to a system to improve that. This is used in airplane design and aerospace all the time, and it's a very useful thing. It forces you to think about something that designers usually don't think about, which is how will my system fail, and will it fail gracefully? Will it fail rarely? Those are critical things to think about when I'm doing system design. Okay, this brief introduction of fault tree analysis, I just scratched the surface. If you type in fault tree analysis and go to the Wikipedia article, it's a good place to start if you really want or need to know more at some point in your job. And where would you find failure rates? Where do you find them? As I said, manufacturers sometimes publish MTBFs. Electronic components, there is a MIL Handbook 217F. you would be amazed. They have so many things listed in there, component failures, how they're going to fail, whether they fail, out of a range, or they fail open, or they fail short, or they do all that kind of thing. This handbook will tell you that. For mechanical components, I found a handbook of reliability procedures for mechanical equipment, and this is quite extensive. By the way, to go back to this Wikipedia article, they tell you the basis of this. It's based naturally in probability theory, and it was developed in the early 60s at Bell Labs, I believe. Okay, I didn't get these failure rates filled in. I believe that the failure rate for an airplane is 1 times 10 to the minus 12 failures per hour for critical faults in planes, while for cars it's 1 times 10 to the minus 15th failures per hour. And why is the acceptable failure rate for a critical fault in an airplane less than for a car? And the reason is, for a car, you have lots more copies, lots more exposure to that potential fault occur. And so essentially what you have is a great big OR gate adding up all the failure rates of all the copies at the end. And so you have to make it better. And so in this case, it's 3 orders of magnitude better than it would be for an airplane. The critical thing about the airplane failure rate and the automobile failure rate is engineers try to design such that that failure will not occur in the service life of the plane or the automobile. And so that critical fault is designed out of the service life of that automobile. Okay, software. Lastly, I just want to talk briefly about software. What do I do with software? If I can't analyze it and determine that it's good, and I generally can't. There are a couple of aerospace languages that Ada and its stripped down subset Spark, where you may be able to do the analysis. But if I can't prove that it's going to work, I have to assume it's failed. This used to be the philosophy of Boeing. Apparently, they've changed it, given the issues they've had on the 737. But it used to be that all software in the plane was assumed failed, and the plane had to be flyable and landable without a running line of code. And the reason is that I can't write bug-free software, and I can't figure out a failure rate of the software, because if I could, I would write bug-free software. So hopefully that's useful to you, and we'll explain the process a little bit. Anyway, talk to you later.